Hey guys, today we're going to talk about the other indeterminate forms that we haven't talked about yet and how we can use L'Hopital's rule to find some of these limits for indeterminate forms. So the first one that we talked about was 0 over 0. And if you have 0 over 0, we saw the proof for this one using L'Hopital's rule. And all you have to do is take the derivative of the top and the derivative of the bottom, and then you evaluate the same limit using the derivatives. So in this case, first thing we have to do is to check to see if it's 0 over 0. So if we check here, we plug in pi over 2. On the top, we have 1 minus sine of pi over 2 is 1, because it's at the top of the circle. That's 1 up there. And on the bottom, we have 1 plus, this would be, 1 plus cosine of pi, which is 1 minus 1 as well, so we have 0 over 0. Okay, so we have this indeterminate form, which means we can use L'Hopital's rule. So we're going to do the derivative of the top. Derivative of negative sine is negative cosine, so I have the same limit. Theta approaches pi over 2. Derivative of the top, we said, is negative cosine of theta. And then on the bottom, we have the derivative of cosine 2 theta, which using chain rule would give us negative 2 sine of 2 theta. So if we plug pi over 2 in, that would give us on the top, cosine of pi over 2 is 0, because it's not left or right. And on the bottom, we have sine of pi, which is also 0. So we have to use L'Hopital's rule again. So using L'Hopital's rule, should put an L here as well. So using L'Hopital's rule, this will be limit as theta approaches pi over 2. Derivative of negative cosine is positive sine of theta. Divided by, now if we chain again, we'll have negative 4 cosine of 2 theta. So if we plug pi over 2 now, we have 1 on the top for sine. And on the bottom, we have negative 4 cosine of pi, which is positive 4, because we have negative 4 times cosine of pi, which is negative 4 times negative 1. So we have positive 4 on the bottom. So our limit is 1/4. There you go, L'Hopital's rule for 0 over 0, kind of the simplest of cases. So now we're getting into infinity over infinity, which we've talked about as well. So if we plug infinity into this guy, natural log of infinity, natural log grows very slowly. In fact, if you graph it on a calculator, it looks like it has a horizontal asymptote, but that's just because e to the x grows so fast, right? E to the x grows so quickly that it looks like it has a vertical asymptote. Same thing with natural log, but really it does go to infinity. So this guy would be infinity on top and infinity on the bottom, because we square root of infinity will just get big as well. The square root function looks kind of like natural log, so it starts at 0, and it also looks like it levels off, but it doesn't. So for this guy, we got infinity over infinity, so we can use L'Hopital's rule. So we're going to do limit as x approaches infinity of derivative of natural log is 1 over x, divided by derivative of 2 root x, that's 2x to the 1/2. The 1/2 will come to the front, cancel out the 2, so we'll just have x to the negative 1/2, so that's 1 over the square root of x. Now I'm going to rewrite this. So this is the limit as x approaches infinity. I'm just going to multiply by the reciprocal of the denominator. So we have root x over x. We plug infinity now, we still have infinity over infinity, so I'll have to do L'Hopital's rule again. So we'll have limit as x approaches infinity of 1 over 2 root x divided by 1. Now we plug in infinity, and that is 0. So something interesting about this problem is that you might have seen, we're going to talk about this in the next section, but the growth rates of these functions, square root grows slowly, but it's faster than natural log. Natural log gets very flat very quickly. Root x, it gets flat, but it's a little bit slower than natural log. So the reason that this turns into 0 is because the bottom function is growing faster than the top. That's all there is to it. So 0 over 0 and infinity over infinity, both of these pretty straightforward L'Hopital problems. Today we're going to get into some more exciting ones. Let's take a look at the next one. So here we have infinity times 0. If we plug in infinity here, we have infinity multiplied by sine of 1 over infinity, which is 0. So that's infinity times 0. Now the trick here is that that never is really going to be 0. It's going to be getting small, but not quite 0. And this x gets very big. So it's kind of like a tug of war to see which one is going to win. So what we have to do here is we're going to rewrite this so that it's in one of the other forms, because I can't do L'Hopital's rule on infinity times 0. It's not even a fraction. So what I'm going to do is I'm going to rewrite this limit to be the limit as x approaches infinity of sine of 1 over x divided by 1 over x. Now you can do the algebra here to convince yourself that these are the same. But if you just multiply by the reciprocal of the denominator, you'll have x times sine of 1 over x. So the reason we do this is that now if we plug in infinity, on the top we have sine of 0 because 1 over infinity will be approaching 0. And then at bottom we have 0. So that's 0 over 0. So now we can use L'Hopital's rule. So the whole reason we rewrite it is so it's in one of those indeterminate forms that works for L'Hopital's rule. So you have the limit as x approaches infinity. Derivative of the top would be cosine of 1 over x times negative 1 over x squared, because we have to chain. On the bottom, the derivative of this is negative 1 over x squared. Hey, that's nice. Cancel the ants. Those are gone. Now we plug in infinity. So we have cosine of 1 over infinity, which is approaching 0. Cosine of 0 is 1. So that's kind of cool. We have a 0 times infinity actually ends up being 1. Now, you might have seen that right here, because as x approaches infinity, this turns into 0, and this turns into 0, and our sine x over x, as x goes to 0, goes to 1. So you might have seen that. So anytime you have infinity times 0, you're just going to rewrite it using fractions, usually. And generally what's going to happen is you have two options. It'll either be 0 over the 1 over infinity. That's what we did here. So sine of 1 over x, as x approaches infinity, is 0. And then we had 1 over infinity on the bottom, because that's 0 over 0. Or you can do the infinity on the top, and on the bottom you can do 1 over the 0, which would be infinity over infinity. Either way, one might be easier than the other. So now we have a subtraction of infinities. Let's see what happens when we plug in 1 here. When we plug in 1, we have 1 over natural log of 1, which is 0. So 1 over 0 is getting close to infinity. And then minus 1 over x minus 1. Well, that's 1 over 0 again, so we have infinity minus infinity. We have infinity minus infinity. What we're going to do is we're going to use our just algebra skills to be able to combine these, and then we should be able to use L'Hopital. So this is not L'Hopital. I'm just rewriting this this rational expression to see what happens. So I'm going to find a common denominator. So we'll have x minus 1 over x minus 1 times ln x. So I just multiply by x minus 1 on the top and bottom there. Then we subtract off ln x over x minus 1 times ln x. So now we have a common denominator that's x minus 1 ln x. We can rewrite this as limit as x approaches 1 of x minus 1 minus ln x divided by x minus 1 times ln x. Now let's plug in 1 and see what happens. On the top, I have 1 minus 0, because natural log of 1 is 0. On the bottom, I have 0 times 0. That's 0 over 0. Hey, that's one of our indeterminate forms we can use L'Hopital on. So here's our L'Hopital's rule. Derivative of the top. Derivative of x is 1. Derivative of negative 1 is 0. Derivative of ln x is 1 over x. So we have 1 minus 1 over x. We have our limit out front. X is approaching 1. On the bottom, we'll have to use product rule. So let's do the derivative of x minus 1, which is 1. So we'll just have ln x by itself. And then plus, let's see, the derivative of ln x is 1 over x. So I have x minus 1 over x. So now if we plug 1 in, on the top we have 1 minus 1, which is 0. And on the bottom we have ln of 1, which is 0, plus 0 again. So we have 0 over 0. So we have to use L'Hopital again. Now this time, the x minus 1 over x, if we break that apart, x over x minus 1 over x, that's 1 minus 1 over x. So I'll make our derivative a little easier on the bottom there. So we'll box that so that we know that that's what that is. So our derivative on the top, the 1 will go away. Derivative of 1 over x is negative 1 over x squared, and we got this negative to cancel it out. So we got 1 over x squared on the top. Get our limit out there. And on the bottom, we have 1 over x. And then this guy, the derivative of this is going to be just 1 over x squared again. So we plug in 1. That's 1 upstairs. On the bottom, we got 1 plus 1, 1/2. I always find that fascinating that you have infinity minus infinity as x goes to 1, and you end up with it being 1/2. Kind of crazy. Okay, so now the last 3 indeterminate forms that we're going to talk about, they involve exponents. So anytime you have an exponent on a function, if you want to get rid of it, there's a function that we use for that. And hopefully we know now that logs will do that. So we're going to see problems like x to the x. Right, we don't like that x in the exponent, so you take the natural log, move the x to the front, so you have x times ln x. Now the issue with this is you can't just take natural logs of functions, right? Because if you take a natural log of a function, it's going to change the structure of the function. So what we do is we say, okay, well, if we take the natural log, how can we get the function back? So let's say we want the limit, let's say f of x is x to the x. Ooh, x to the x. There we go. So if we want the limit as x approaches whatever value, a, of f of x, what we're going to do is we're going to say, okay, let's take the natural log of it. So instead of just taking the natural log, though, basically what we want to do is you want to do the limit as x approaches a of e to the natural log of f of x. So since e and natural log are inverse functions, we haven't changed it at all. So all we've done is we've done inverse functions here of each other. So that'd be like adding to and subtracting to. I mean, we're just doing inverse functions of each other, so this is still the same thing. So then, one of the limit properties we learned is that you can just throw this up into the exponent. So e to the limit as x approaches a of ln of f of x. So what this means is what we're going to do is we're going to find the limit that happens just when you do the natural log of f of x. And then after you have this, your answer is going to be e to the L. Okay, so that's this last step. So we find the limit of the natural log, and that'll allow us to like move the x to the front, which will be nice. And then after we have that, we just do e to that power, and then we'll have our answer. Let me show you an example. So one of the infinities is kind of interesting because, like for this one, as x goes to infinity, this is going to get close to 0, but it never really gets there. And this is getting really, really big. But the question is, if this is turning into 0, then you have 1 to a power, which would be 1. But if this gets big fast enough, then it's going to make some number out of this. So it's kind of a little bit of a tug of war trying to figure out which one's going to win. And if we plug in infinity, we see that we have 1 plus 0, which is 1, raised to the infinity power. Okay, so we're going to see which one wins. So we're going to take the natural log. So we're going to find L, which is the limit as x approaches infinity, of natural log of 1 plus 1 over x to the x power. And then after we find this limit, what's our last thing we're going to do? We're going to put it on top of the e. And then that'll be our answer. So let's see if we can figure this out. We're going to move the x to the front. So we have limit as x approaches infinity, x times ln of 1 plus 1 over x. That's just a log property. Now let's see what we have. We have infinity times natural log of 1, which is infinity times 0. Hey, that's one of our indeterminate forms. We should be able to write this now so that we have a 0 over a 0 or an infinity over an infinity. I think the trick to that is going to be writing it ln of 1 plus 1 over x divided by 1 over x. So we had x over here, we're divided by 1 over x. That's the same exact thing because you multiply by the reciprocal. That's the limit as x approaches infinity. So now we have, on the top we have 0, on the bottom we have 0, so we can use L'Hopital. Derivative of the top, 1 over 1 plus 1 over x. That's derivative of natural log. And then times derivative of the inside, which is negative 1 over x squared. Then on the bottom, this is all limit, as x approaches infinity. On the bottom, the derivative of 1 over x is negative 1 over x squared. Hey, nice, these cancel again. So now we plug in infinity. We have 1 over 1 plus 0, which is 1. This is not our answer, though, because what do we have to do last? We're going to do e to that power. So our actual limit, this guy right here, is e to the first power, or e. Now, some of you might have recognized this is the definition of e. I mean, that's how you define e. So you let x go to infinity, 1 plus 1 over x to the x power. But it's cool to see that it works out with L'Hopital. So we have 0 to the 0, same idea. The problem here is that 0 to any number is 0, but any number to the 0 is 1. So is this going to be 1 or 0, or is it going to be something in between? In one of my classes, someone suggested, well, can you just average them and say it's 1/2? No, you cannot do that, okay? So we have to use our logarithmic limits here to find L'Hopital. So let's give it a shot. So we got limit as x approaches 0 from the right, of natural log of x to the x, and then we'll get this limit, and we'll do e to that power. So we move the x to the front, so we have limit as x approaches 0 from the right, x ln x. So if we plug in 0, we have 0 times natural log of 0 from the right, so natural log looks like this. So as it approaches 0 from the right-hand side, it's going to negative infinity. So 0 times negative infinity. I'll figure out the negative later. But for now, we know that what we have to do is we have a 0 times an infinity, so we're going to rewrite it with like a 1 over x. So we have limit x approaches 0 from the right of ln x over 1 over x. So now in this case, when I plug in 0 on the top, I have a negative infinity. On the bottom, I have a positive infinity. So infinity over infinity allows me to do L'Hopital's rule. Remember again, natural log as x approaches 0 from the right-hand side, going down to that negative infinity. So this is limit x approaches 0 from the right-hand side. Derivative of natural log is 1 over x. Derivative of 1 over x is negative 1 over x squared. So that's the limit as x approaches 0. Let's do a little algebra here. If we multiply by the reciprocal, we have negative x squared over x. That goes away, that goes away. So we have limit as x approaches 0 of negative x. That is 0. Is that my answer? No, because I have to plug it back into e. So I do e to the 0 power, which is 1. Cool. Fun to look at these graphically as well if you want to graph them on Desmos. All right, last one. We got infinity to the 0 power. Now here the issue is that anything to the 0 is 1, but if that infinity is getting big fast enough and the 0 isn't getting low fast enough, then it's not going to work out. So let's see here. Let's take the natural log. So limit x approaches infinity, natural log of x to the 1 over x. Let's double check here first. You plug in infinity, you get infinity here, and then you get the 0 power here, so that checks out. Okay, so move that 1 over x to the front. Limit as x approaches infinity of 1 over x ln x. Now this guy is kind of a weird one, because if we plug in infinity, we have 0 out here, and we have infinity right here. But if you slide this guy, oh sorry, as x approaches infinity, what's going on here? Yes, 0 times infinity. 0 times infinity is what we have, because now we're going to use the indeterminate form. So if you just slide the ln x right on top, you have infinity over infinity. So all we're doing here is just rewriting this. Lim as x approaches infinity of ln x over x. You can also think about that as dividing by the reciprocal of 1 over x, but that seems like too much thinking. So this is infinity over infinity, which means we can now use L'Hopital. So we have limit as x approaches infinity of 1 over x divided by 1. Well, when you plug infinity to 1 over x, you get 0. So e to the 0, 1. Cool. All right, so let's take a look at everything we have. So there are 7 indeterminate forms we've talked about. 0 over 0 and infinity over infinity, you just go straight to L'Hopital. So you have that, you take the derivative of the top, the derivative of the bottom, reevaluate your limit. Infinity times 0, you're going to rewrite your expression probably as infinity over 1 over 0 or 0 over 1 over infinity, because then you have, this would be an infinity over infinity, so 0 down there. And this guy over here would be a 0 over 0. Either one of those will allow you to do L'Hopital's rule. Oh, for L'Hopital. Infinity minus infinity, you're going to find a common denominator. You're going to combine your fractions, or combine whatever terms you have. And at that point, you should be able to use L'Hopital. The last 3 all use logarithms. So we're going to do natural log of f of x. So you're going to do ln of f of x. Find the limit of that guy. And then your last thing you're going to do is you're going to do e raised to that limit. So whatever that limit was, you're going to do e to that power, and that'll give you the correct limit. So hopefully this was helpful. Give the homework a shot. Love you guys. That's why I'm here. Have a great day.